For decades, a small machine has been moving through darkness far beyond the planets. It no longer sees Earth. It no longer sees the Sun the way we do. Yet it is still listening. On August 25, 2012, something quiet but historic happened. A spacecraft launched in 1977 slipped past the invisible boundary where the Sun's influence fades and interstellar space begins. No celebration followed. No dramatic signal. At the time, no one even noticed the exact moment it crossed. The spacecraft was NASA's Voyager 1. It continued drifting outward at nearly 17 kilometers per second, carrying instruments designed in the early 1970s technology built before most modern computers existed. For years after the crossing, Voyager 1 moved through what scientists believed would be a calm region between stars. But then the spacecraft started hearing something unexpected. Not with microphones, with plasma sensors. Tiny disturbances began passing through the surrounding gas waves, moving through charged particles scattered between stars. The signals were faint but measurable. Each one left a pattern in the spacecraft's plasma wave instrument, a detector that measures vibrations in ionized gas. When researchers examined the data back on Earth, they noticed something strange. The density of plasma around Voyager 1 wasn't behaving the way models predicted. Instead of remaining relatively stable, it kept increasing the farther the spacecraft traveled from the Sun. In 2013, the first clear measurement arrived, then another, and another. Each time Voyager 1 recorded a passing plasma shockwave, scientists could measure the density of the surrounding interstellar medium. Each time the number came back slightly higher than expected. By 2020, the pattern had become difficult to ignore. The space between stars once thought to be extremely thin and uniform appeared to be gradually compressing along Voyager's path. The change wasn't dramatic, but it was measurable. And measurable changes in interstellar space are not supposed to happen casually, because between stars, nothing moves quickly. Nothing changes quickly, which leads to the anomaly that now sits at the center of this investigation. Voyager 1 is detecting plasma waves that reveal a steadily increasing density in the interstellar medium beyond the Sun's heliosphere. The question is simple. What is compressing the space between stars? To understand that signal, we have to follow Voyager's journey outward past the planets, beyond the Sun's magnetic bubble, and into a region humanity has never measured directly before, because Voyager 1 is still moving, still listening, and every few years the silence between stars sends back another wave. We're about to follow it. In the summer of 1977, long before smartphones, GPS satellites or modern computers, engineers at NASA were preparing to launch a machine that would eventually leave the solar system. At the time, that was not the plan. The mission was supposed to last 4 years. The spacecraft would visit Jupiter and Saturn, send back images, measure their magnetic fields, study their moons, and then continue drifting outward until its systems slowly failed. That was the expectation. Nothing more. But the opportunity that launched Voyager 1 was rare. Once every 176 years, the giant planets align in a configuration that allows a spacecraft to use their gravity like stepping stones. By carefully approaching each planet at the right angle, a spacecraft can steal a tiny fraction of its orbital energy and fling itself toward the next destination. The method is called gravity assist. Instead of carrying enormous fuel reserves, Voyager could use the motion of planets themselves to accelerate. The trajectory was calculated years in advance using early computer simulations. The numbers showed something remarkable. A spacecraft launched in 1977 could reach Jupiter, then Saturn, and potentially even Uranus and Neptune using this natural gravitational chain. NASA approved the mission. 2 spacecraft were built. They were named Voyager 1 and Voyager 2. Despite the numbering, Voyager 1 actually launched second on September 5, 1977 from Cape Canaveral, Florida aboard a Titan IIIe rocket. The spacecraft weighed 722 kilograms. Its design reflected the engineering philosophy of the early space age: durable, simple, and redundant wherever possible. Systems were duplicated so that if one failed, another could take over, because once Voyager left Earth, there would be no repairs. The spacecraft carried 11 scientific instruments. Among them were cameras for planetary imaging, magnetometers to measure magnetic fields, detectors for cosmic rays, and one instrument that would later become unexpectedly important: the plasma wave subsystem. At the time, it was intended mainly to study charged particles around planets. No one expected it would one day measure the environment between stars. Voyager also carried something unusual. Attached to its side was a gold-plated copper disc, about 30 centimeters in diameter. It is known today as the Golden Record. Etched into the disc are 115 images, greetings spoken in 55 human languages, recordings of natural sounds from Earth, and a collection of music from different cultures. There are instructions engraved on the cover showing how to play the record, using symbols that scientists hoped another civilization could understand. The idea was simple: if Voyager were ever discovered by intelligent life in the distant future, the record would act as a small introduction to Earth. At launch, that idea felt symbolic more than practical. After all, the spacecraft was expected to operate only a few years. Then the mission began. Voyager 1 reached Jupiter in March 1979. The images stunned scientists. The spacecraft photographed massive storms swirling across the planet's atmosphere, including the Great Red Spot, a hurricane larger than Earth itself. But the most surprising discovery came from one of Jupiter's moons, a small moon called Io. Images revealed towering plumes rising hundreds of kilometers above its surface. They were volcanic eruptions. Until that moment, active volcanoes had never been observed anywhere beyond Earth. Io became the first known example of active geology on another world. Voyager 1 continued outward. In November 1980, it arrived at Saturn. The spacecraft captured detailed images of Saturn's rings and discovered complex structures within them: thin braided strands, gaps carved by small moons, and gravitational waves rippling through the icy particles. It also passed close to Titan, Saturn's largest moon. Titan's atmosphere was so thick that cameras could not see its surface, but instruments measured nitrogen and methane in the atmosphere, hinting that Titan might have complex organic chemistry. After the Saturn encounter, Voyager 1's path bent sharply upward relative to the plane of the solar system. This maneuver allowed the spacecraft to pass close to Titan, but it also meant Voyager 1 would not continue toward Uranus and Neptune. That role fell to Voyager 2, which followed a slightly different path. Voyager 1 was now headed toward the outer edge of the Sun's domain. At that distance, sunlight becomes weak. Solar wind, the constant stream of charged particles flowing outward from the Sun, also begins to thin. Scientists knew that somewhere far ahead there must be a boundary where the solar wind slows and collides with the gas that fills the galaxy. But in the early 1980s, the location of that boundary was uncertain. Some estimates placed it at 50 astronomical units from the Sun. Others suggested it might lie beyond 100 AU. For reference, 1 AU is the distance from Earth to the Sun, about 150 million kilometers. Voyager 1 was moving steadily outward. By the mid-1990s, it had passed 50 AU. Its cameras had long since been shut down to conserve power, but other instruments continued sending measurements back to Earth. Every command from mission control required patience. Radio signals travel at the speed of light, but distance still matters. By the late 1990s, a message sent from Earth took more than 10 hours to reach the spacecraft. Voyager's antenna then transmitted its reply back across the solar system using a 23-watt transmitter. roughly the power of a refrigerator light bulb. Those signals were received by NASA's Deep Space Network, a global system of giant radio antennas located in California, Spain, and Australia. Together they formed a listening network capable of detecting faint transmissions from billions of kilometers away. Year after year, Voyager 1 continued drifting outward, past Pluto's orbit, past the region of icy objects known as the Kuiper Belt. Then, in the early 2000s, its instruments began detecting something new. The solar wind around the spacecraft started slowing down. This region is known as the termination shock. It forms where the solar wind, traveling outward at hundreds of kilometers per second, begins to feel the pressure of the surrounding interstellar medium. Like ocean waves crashing against a shoreline, the particles slow, compress, and become turbulent. Voyager 1 crossed the termination shock in December 2004, about 94 AU from the Sun. Beyond that point lay the outermost layer of the heliosphere, a region called the heliosheath. The heliosheath is chaotic. Solar wind particles swirl and mix with particles from interstellar space. Magnetic fields twist and stretch. The environment becomes unpredictable. For nearly 8 years, Voyager 1 moved through this turbulent region. Then, gradually, the signals began changing again. Solar particles became less common. Galactic cosmic rays, high-energy particles from distant supernova explosions, began increasing sharply. Something important was happening. On August 25, 2012, Voyager 1 crossed a boundary scientists had debated for decades. The spacecraft passed beyond the heliopause, the outer edge of the Sun's magnetic influence. For the first time in history, a human-built object had entered interstellar space. At a distance of about 121 astronomical units from the Sun. But the crossing did not produce fireworks. There was no dramatic event, just a quiet shift in data. Cosmic rays increased, solar particles dropped, magnetic fields changed direction. And something else appeared, faint vibrations in ionized gas surrounding the spacecraft. They were plasma waves. At first they seemed insignificant, small disturbances passing through the thin gas between stars. But each wave carried information. Each one revealed something about the environment Voyager had just entered. And when scientists began calculating what those waves meant, they noticed a number that didn't quite fit expectations. The density of the interstellar plasma around Voyager was higher than predicted, not by a huge amount, but enough to raise a question. Because between stars, space is supposed to be quiet, almost empty. Yet Voyager had just started hearing something moving through that emptiness, something capable of compressing the gas between stars. And that was only the beginning of the measurements. From Earth, the Sun feels permanent. Every day it rises with the same familiar brightness. Its light reaches us in just over 8 minutes, warming oceans, powering weather, feeding forests and cities alike. For most of human history, the Sun appeared to sit alone in space, a solitary star surrounded by planets. But the Sun is not isolated, it is constantly breathing outward. From the surface of the Sun, an enormous stream of charged particles flows in all directions. Electrons and protons escape the solar atmosphere and accelerate into space, carried by heat and magnetic turbulence from the outer solar corona. This outward flow is called the solar wind. Near Earth, the solar wind moves at roughly 400 kilometers per second, though bursts of faster wind can exceed 800 kilometers per second during active periods of the Sun. At those speeds, the solar wind does something remarkable. It inflates a gigantic bubble around the entire solar system. This bubble is not visible. It cannot be seen with telescopes or cameras. Yet it surrounds every planet and stretches far beyond the orbit of Pluto. Inside this region, the environment of space is shaped primarily by the Sun. Scientists call this vast structure the heliosphere. You can imagine it as something like the atmosphere of a star, except it extends across distances measured not in kilometers but in billions of kilometers. The heliosphere is created because the solar wind pushes outward against the thin gas that fills the galaxy. That gas, known as the interstellar medium, contains sparse atoms of hydrogen and helium drifting between stars. The two regions meet at a distant boundary, but the meeting is not calm. As the solar wind travels farther from the sun, it spreads out and gradually loses pressure. Eventually, it encounters resistance from the surrounding interstellar gas and magnetic fields. The outward flow cannot continue smoothly forever. Instead, it slows down. The first major slowdown occurs at a region called the termination shock. Here, the solar wind abruptly drops from supersonic speeds to slower, turbulent motion. Particles compress. Magnetic fields twist and tangle. The solar wind, which once streamed outward freely, begins to pile up against the invisible pressure of the galaxy beyond. Voyager 1 detected this transition in December 2004. At the time, the spacecraft was about 94 astronomical units from the Sun, more than twice the distance of Pluto's orbit. Instruments recorded sudden changes in particle speeds and magnetic behavior, evidence that the spacecraft had entered a new region of space. Beyond the termination shock lies a vast transitional zone called the heliosheath. The heliosheath is not quiet. It is filled with slowed solar wind, swirling magnetic turbulence, and particles that have bounced back from the boundary ahead. Solar particles and interstellar particles begin interacting here in complicated ways. Some are deflected. Others become trapped in magnetic loops. The region behaves a little like the frothy edge of a wave breaking on a shoreline. For Voyager 1, this region lasted years. As the spacecraft moved deeper through the heliosheath, instruments observed dramatic shifts in particle populations. Solar wind particles became less dominant. At the same time, high-energy particles from outside the solar system began appearing more frequently. These particles are known as galactic cosmic rays. Cosmic rays originate from violent events across the Milky Way, exploding stars, shock waves from supernova remnants, and powerful magnetic fields near stellar debris. They travel across the galaxy at nearly the speed of light, sometimes for millions of years before encountering obstacles. The heliosphere normally shields the inner solar system from many of these particles, but near its outer edge, that protection weakens. Voyager's detectors began registering an increase in cosmic rays as it approached the boundary ahead. Scientists watching the data began to suspect something important was near, because beyond the heliosheath lies the final frontier of the Sun's influence. The heliopause. The heliopause marks the location where the outward pressure of the solar wind finally balances the pressure of the interstellar medium. It is not a wall. There is no sharp physical barrier. Instead, it is a contact surface where two enormous flows of plasma meet. Inside the heliopause, solar particles dominate. Outside it, the environment belongs to the galaxy. Crossing this boundary had long been a theoretical milestone. For decades, scientists debated where it might lie. Estimates range widely. Some suggested it could be around 100 AU, while others believed it might be much farther. The problem was simple. No spacecraft had ever reached it. Voyager 1 was the first machine capable of doing so. By the early 2010s, the spacecraft had traveled more than 17 billion kilometers from Earth. Signals from Voyager now took over 16 hours to reach mission control. Engineers still communicated with the spacecraft through NASA's Deep Space Network, whose massive radio dishes quietly tracked Voyager's faint transmissions across interplanetary space. Meanwhile, scientists watched the incoming data carefully. Gradually, the pattern began shifting. Solar wind particles continued dropping. Cosmic rays continued rising. Magnetic field readings showed subtle changes. Then something curious happened. Voyager's plasma science instrument, designed to measure solar wind density directly, had stopped working years earlier. The instrument failed in 1980, shortly after the Saturn encounter. That meant Voyager could no longer directly measure plasma density around it. For years this seemed like a serious limitation, but another instrument remained active: the plasma wave subsystem. This detector measures tiny oscillations in electric fields caused by vibrations in ionized gas. Normally these signals appear during interactions with planetary magnetospheres or solar disturbances. In deep space, scientists expected the instrument to remain mostly quiet, yet in April 2013 a signal appeared. A faint tone in the plasma wave instrument. When scientists converted the frequency of the signal into plasma density, a known relationship in plasma physics, they discovered something unexpected. The surrounding medium was far denser than solar wind. In fact, the density matched predictions for interstellar space. The signal had been triggered by a shock wave traveling outward from the Sun, likely caused by a solar eruption months earlier. When the shock reached Voyager's location, it compressed the surrounding plasma and caused it to vibrate. Those vibrations produced the signal, and the signal revealed the environment Voyager had entered. That moment provided the clearest confirmation that Voyager 1 had crossed the heliopause. Humanity had officially reached interstellar space. Yet the discovery came with a surprise. The interstellar medium surrounding Voyager appeared denser than many models predicted. Instead of the extremely thin gas scientists expected, the measurements suggested a region where particles were packed slightly closer together. The difference was small, but in astrophysics, small differences often point to larger forces at work. And Voyager was still moving. At roughly 17 kilometers per second, the spacecraft continued drifting deeper into the interstellar medium, a region never directly measured before. Every year it traveled another 500 million kilometers farther from the Sun. Every year its instruments continued listening. At first the plasma waves appeared only occasionally, but over time something began changing. The density readings derived from those waves were not remaining constant. Instead, with each new measurement, the numbers crept upward. Slowly, quietly. The deeper Voyager traveled into interstellar space, the thicker the surrounding plasma appeared to become. That observation raised a difficult question. Because the region Voyager entered, part of the local interstellar cloud surrounding our solar system, was thought to be relatively uniform. Yet Voyager's measurements suggested otherwise. Something was compressing the plasma between stars. The waves Voyager detected were not random noise. They were signals moving through a medium that seemed to be gradually changing. And that meant the story of Voyager's journey had entered a new phase. Because measuring the density of space between stars is not simple. It requires careful interpretation of faint signals, rare shockwaves, and instruments designed decades before the spacecraft ever left the solar system. To understand what Voyager is actually hearing, we need to look more closely at how scientists measure the invisible gas that fills the galaxy. Because in deep space, even silence has structure. When Voyager 1 finally crossed into interstellar space, no alarms sounded in mission control. There was no sudden signal telling scientists the spacecraft had passed the Sun's final boundary. No sharp transition appeared on a monitor. The moment happened quietly, almost invisibly, buried inside streams of numbers arriving from a machine more than 18 billion kilometers away. At the time, no one realized it had already happened. The spacecraft continued transmitting the same kinds of measurements it had been sending for years. Particle counts, magnetic field readings, faint signals from instruments that had been operating since the late 1970s. Each transmission traveled outward from Voyager's small antenna at 23 watts, crossing the solar system for more than 16 hours before reaching Earth. By the time those signals arrived at NASA's Deep Space Network, they were incredibly faint. The radio waves carried less power than the static produced by a household appliance. Detecting them required enormous antennas, dishes 70 meters wide, listening carefully across quiet stretches of radio spectrum. inside laboratories and data centers, scientists began examining the numbers. The first clue appeared in cosmic ray measurements. Voyager carried detectors designed to measure high-energy particles arriving from outside the solar system. For decades, these detectors recorded only modest numbers because the heliosphere, the Sun's magnetic bubble, shields the inner solar system from much of the galaxy's radiation. But around May 2012, something began shifting. The number of cosmic rays detected by Voyager began rising sharply. At the same time, particles originating from the Sun began dropping. This reversal was strange. Inside the heliosphere, solar particles dominate. Outside it, cosmic rays from the galaxy become far more common. Seeing those two trends move in opposite directions suggested that Voyager was approaching a boundary where the Sun's protection was fading. Scientists watched carefully as the pattern continued. By August 2012, the shift became dramatic. Solar particles nearly disappeared from Voyager's instruments. Cosmic rays surged to levels never previously recorded during the mission, but there was still uncertainty. Another measurement was needed. The heliopause, the boundary between solar and interstellar space, should also show a change in magnetic field behavior. The Sun's magnetic field extends outward through the solar wind, but beyond the heliopause, the dominant magnetic environment belongs to the galaxy itself. If Voyager had truly crossed the heliopause, the magnetic field direction should rotate significantly. Yet when scientists examined Voyager's magnetometer data, the expected rotation did not appear clearly. Instead, the magnetic field direction remained surprisingly similar. That inconsistency created months of debate. Some researchers believed Voyager had entered a new region still connected to the heliosphere. Others suspected the spacecraft had already crossed the heliopause, but the magnetic geometry was more complicated than expected. The answer came from an instrument few people had been thinking about: Voyager's plasma wave subsystem. Unlike many of the spacecraft's other sensors, the plasma wave detector does not measure particles directly. Instead, it listens for tiny oscillations in electric fields caused by vibrations within ionized gas plasma. These vibrations behave a little like sound waves moving through air, but in space, the frequencies depend on the density of the surrounding plasma. When plasma becomes compressed, the oscillation frequency increases. By measuring that frequency, scientists can calculate the number of charged particles in the surrounding environment. In April 2013, researchers examining Voyager's data discovered something remarkable. Months earlier, the spacecraft had recorded a clear plasma wave signal. It lasted several weeks. The signal was not caused by Voyager itself. Instead, it had been triggered by a shock wave from a solar eruption that had traveled outward through the heliosphere. When the shock reached Voyager's location, it compressed the surrounding plasma and caused it to oscillate. Those oscillations produced a faint tone inside the plasma wave instrument. When scientists measured the frequency, they calculated the plasma density surrounding Voyager. The result came out to roughly 0.08 electrons per cubic centimeter. That number mattered because inside the heliosphere, solar wind plasma is extremely thin, typically around 0.02 electrons per cubic centimeter at Voyager's distance. But in the interstellar medium, plasma density is expected to be much higher. The number Voyager recorded matched predictions for interstellar space. The spacecraft had already crossed the heliopause months earlier. The moment had occurred on August 25, 2012. But it took nearly a year for scientists to confirm it. When the announcement was finally made in September 2013, Voyager 1 officially became the first human-built object to enter interstellar space. The achievement was historic. For the first time in human history, a spacecraft had directly measured the environment between stars. Yet the discovery also revealed something unexpected. The plasma density outside the heliosphere was denser than many earlier models predicted. Instead of an extremely thin gas gradually blending into the solar wind, The measurements suggested a sharper transition between the sun's bubble and the surrounding interstellar medium, but even more surprising was what happened next. Voyager kept listening. Over the following years, additional plasma wave signals appeared in the spacecraft's data. Each one was triggered by another distant solar eruption, sending shock waves outward through space. Each time the shock reached Voyager, it briefly compressed the surrounding plasma, and each time scientists used the oscillation frequency to calculate the density of the interstellar medium. The numbers began forming a pattern. In 2014, the density measurement increased slightly. In 2015, it increased again. The trend continued. The farther Voyager traveled from the heliopause, the denser the surrounding plasma appeared to become. The change was not dramatic, but it was consistent. Space between stars is often described as empty. In reality, it is filled with extremely thin gas and magnetic fields that stretch across enormous distances. Even tiny variations in density can reveal large-scale structures inside that environment. Shock fronts, magnetic pressure zones, or regions where gas clouds interact. Voyager was now moving through one of those structures. The spacecraft itself could not see it. There are no cameras operating anymore. No images of the region beyond the heliosphere. The environment surrounding Voyager exists only in the form of measurements, particle counts, magnetic readings, and faint electrical vibrations. Yet those signals describe a landscape, a region where the sun's influence fades into the wider galaxy, where interstellar gas drifts slowly through space, shaped by magnetic forces and distant stellar explosions. Voyager is traveling through that region now. At a speed of 17 kilometers per second, it moves farther from the sun every hour. Every year, the spacecraft travels roughly 520 million kilometers deeper into interstellar space. And every so often, another shockwave from the sun catches up with it. When that happens, the surrounding plasma vibrates again. The instrument listens, and the density of the space between stars reveals itself, one wave at a time. So far, we know Voyager has crossed the heliopause. We know the plasma around it is denser than expected. But those measurements only raise another question, because space between stars should not gradually thicken without a cause. Something must be compressing that gas, and to understand that signal, scientists had to learn how Voyager's instruments were turning faint vibrations into a map of the interstellar medium, because in deep space, even the smallest wave can carry the shape of an invisible structure. For a long time after Voyager 1 crossed into interstellar space, the spacecraft drifted through silence, not complete silence. Space is never truly empty, but the instruments detected nothing dramatic. No sudden storms, no violent particle bursts, just the steady background of cosmic radiation arriving from distant regions of the Milky Way. Voyager itself could not actively measure the density of the surrounding plasma anymore. The plasma science instrument, which had once measured solar wind particles directly, stopped working in 1980 after the Saturn encounter. For years that failure seemed unfortunate, but it turned out Voyager still had another way to measure the environment. It just required patience. Because the interstellar medium reveals itself only when something disturbs it. The disturbance arrived from the sun. In March 2012, months before Voyager officially crossed the heliopause, a powerful coronal mass ejection erupted from the sun's surface. These eruptions occur when twisted magnetic fields in the solar corona suddenly release enormous amounts of energy. Billions of tons of plasma are launched into space. The expanding cloud travels outward through the solar system as a shock wave, moving faster than the surrounding solar wind. Closer to Earth, such eruptions can cause geomagnetic storms, auroras, and disruptions to satellites. But the shock does not stop there. It keeps traveling outward, gradually weakening as it spreads through space. Yet the solar system is enormous. A shock wave launched from the sun may take over a year to reach the outer boundary of the heliosphere. In early 2013, that particular shockwave finally reached Voyager 1 at the spacecraft's location, roughly 122 astronomical units from the Sun. The wave encountered a new environment, the interstellar plasma surrounding the heliosphere. When the shock arrived, it briefly compressed the gas around Voyager. Charged particles were squeezed closer together, and something inside that plasma began to vibrate. The vibrations were not audible in the usual sense, but electrically they behaved like a tone, a repeating oscillation in the plasma's natural frequency. Voyager's plasma wave subsystem detected the signal immediately. The instrument consists of two wire antennas extending from the spacecraft. These antennas measure fluctuations in the surrounding electric field. When plasma oscillates, it produces a characteristic frequency that depends directly on the density of electrons in the gas. The relationship between frequency and density is well understood in plasma physics. Higher density plasma produces higher oscillation frequencies, so when the shock compressed the plasma, the vibration frequency revealed how many electrons were present in the surrounding medium. The signal recorded by Voyager lasted about 40 days. It appeared in the data as a narrow band of frequencies gradually drifting over time. Back on Earth, scientists analyzed the numbers. The calculation produced a value of roughly 0.08 electrons per cubic centimeter. That number was important for two reasons. First, it confirmed that Voyager had indeed entered interstellar space. Inside the heliosphere, solar wind density is much lower at that distance, usually closer to 0.02 electrons per cubic centimeter. Second, the value provided the first direct measurement of plasma density beyond the heliopause. For decades, astronomers had estimated the density of the local interstellar medium using indirect observations, spectroscopy of distant stars, absorption lines in ultraviolet light, and theoretical models of nearby gas clouds. But those measurements described averages across large distances. Voyager was providing something different, a direct local measurement. And the number was slightly higher than many models predicted, not dramatically higher, but noticeable. That alone might not have been enough to cause concern. Interstellar space is not perfectly uniform, and small variations in density are expected. Gas clouds drift through the galaxy, influenced by magnetic fields and shock waves from ancient supernova explosions. But the story did not end with that first signal. Voyager kept traveling outward. At 17 kilometers per second, the spacecraft was moving roughly 3.6 astronomical units per year, about the distance from the Sun to the asteroid belt every 12 months. For more than a year after the first measurement, nothing unusual appeared. Then another solar eruption sent a shockwave racing outward through the heliosphere. Eventually, it reached Voyager. Again, the surrounding plasma compressed. Again, instrument recorded oscillations. When scientists calculated the density from the new signal, they noticed something subtle. The value had increased slightly. Instead of 0.02 electrons per cubic centimeter, the number appeared closer to 0.09, a small difference, but enough to raise an eyebrow, because Voyager had moved only a few billion kilometers farther into interstellar space. That distance is tiny compared to the scale of the galaxy. Scientists initially assumed the change might simply reflect natural turbulence in the interstellar medium. After all, the region surrounding the solar system is part of a structure called the Local Interstellar Cloud, a drifting cloud of gas roughly 30 light-years wide that the Sun is currently passing through. Gas clouds are rarely uniform. Density can vary from place to place. Still, researchers began paying closer attention to the next signal. It arrived a few years later. Another solar eruption produced another shock wave. The wave traveled outward for months, eventually reaching Voyager again. The plasma compressed. The instrument listened, and the density measurement increased once more. Now the number approached 0.11 electrons per cubic centimeter. The pattern was becoming difficult to ignore. Each time Voyager detected a plasma wave triggered by a passing shock, the surrounding density appeared slightly higher than before. The spacecraft was moving deeper into interstellar space, and the gas around it seemed to be gradually thickening. In astrophysical terms, the difference might still appear small. Even at 0.11 electrons per cubic centimeter, the interstellar medium is extraordinarily thin compared to anything on Earth. A laboratory vacuum chamber contains far more particles than this region of space, yet relative changes matter. A steady increase suggests the spacecraft may be moving into a region where interstellar gas is being compressed by larger forces. Possibilities began forming. Perhaps the heliosphere itself is distorting nearby plasma over vast distances. Perhaps the sun's motion through the local interstellar cloud creates a bow-shaped compression region. Or perhaps magnetic fields threading through the cloud are squeezing the plasma in ways scientists had not fully modeled. At that stage, no single explanation was certain. What was certain was the data. Voyager was measuring a trend, and the trend suggested that the space between stars was not as smooth and uniform as once believed. Instead, it appeared structured, shaped by invisible forces. Every time a solar shockwave reached Voyager, the surrounding plasma briefly revealed its density. Like dust illuminated by a flash of light in a dark room, those flashes were rare. Sometimes years passed between them. But each one added another measurement, another point along Voyager's path, another clue about the structure of interstellar space just beyond the sun's protective bubble. So far, we know the heliopause marks a sharp transition between solar and interstellar environments. We know Voyager's instruments can measure plasma density through wave vibrations, and we know those density measurements are rising. But understanding why requires looking more closely at how scientists interpret those vibrations, and how a spacecraft built in the 1970s can turn faint electrical signals into a map of the invisible gas between stars. Because in deep space, measurement often begins with listening. The space around Voyager 1 cannot be seen. There are no images of the region beyond the heliosphere. The spacecraft's cameras were turned off in 1990 to conserve power, long before Voyager reached interstellar space. Since then, everything scientists know about the environment around the spacecraft comes from instruments that measure invisible signals. Particles, magnetic fields, radiation, and sometimes faint vibrations in plasma. Those vibrations are the key to understanding the structure of the space between stars. To see how they work, imagine a calm lake. If the water is completely still, it is difficult to judge how deep it might be or what lies beneath the surface. But if a stone falls into the water, ripples spread outward. The speed and shape of those ripples reveal properties of the water itself, its density, its depth, its boundaries. Something similar happens in plasma. Plasma is not just gas, it is gas whose atoms have lost electrons, leaving charged particles that respond strongly to electric and magnetic fields. When plasma becomes disturbed, those charged particles can oscillate collectively, producing waves that travel through the medium. These are called plasma oscillations. Their behavior is predictable. The frequency of the oscillation depends on how many electrons are present in a given volume of space. When the electron density is higher, the oscillation frequency increases. When the plasma becomes thinner, the frequency drops. This relationship is one of the fundamental principles of plasma physics, and Voyager 1 carries an instrument specifically designed to measure it. The plasma wave subsystem, often abbreviated as PWS, was built to detect electric field fluctuations in the surrounding environment. Two thin wire antennas extend from the spacecraft, each about 10 meters long. Together they form a simple detector capable of sensing extremely small electrical variations in the plasma around Voyager. Under normal conditions in deep space, the instrument records very little. The interstellar medium is extremely quiet. But when a disturbance arrives, such as a shock wave traveling through plasma, the gas becomes compressed and begins to oscillate. The antennas detect those oscillations as changes in electric field strength. Inside the spacecraft, the instrument converts the signal into a spectrum of frequencies. Back on Earth, scientists examine that spectrum, and from those frequencies, they calculate the density of the surrounding plasma. The mathematics behind the measurement is straightforward for plasma physicists. The oscillation frequency, known as the plasma frequency, depends directly on the number of free electrons per cubic centimeter. Once the frequency is measured, the density can be calculated using well-established equations. This method works even when the spacecraft cannot directly sample particles. That is why Voyager's plasma wave instrument became so important after the original plasma detector failed decades earlier. Without it, scientists would have had far less information about the region beyond the heliosphere. Still, the method has a limitation. Plasma oscillations usually occur only when the plasma is disturbed, and disturbances in deep space are rare. The interstellar medium surrounding the solar system is extremely calm. It consists mostly of hydrogen atoms and ions drifting slowly through the galaxy. Typical particle densities are only about 0.05 to 0.1 atoms per cubic centimeter. For comparison, the air in a room on Earth contains roughly 10 quintillion molecules per cubic centimeter. Interstellar space is therefore almost unimaginably empty, yet it is not completely uniform. Within this thin gas exist magnetic fields stretching across vast distances. These fields influence how particles move, forming structures that are difficult to detect without direct measurement. Voyager's plasma wave instrument allows scientists to probe that structure indirectly. Each time a solar shock wave travels outward from the Sun and reaches the spacecraft, it briefly compresses the surrounding plasma. The compression triggers oscillations. Those oscillations produce measurable frequencies, and the frequencies reveal the local density of interstellar plasma. Over time, a series of these measurements builds a profile of the environment along Voyager's path. This method has produced some of the most important discoveries about the region beyond the heliopause. The first confirmed signal appeared in April 2013, triggered by a solar eruption that occurred months earlier. When scientists calculated the plasma frequency from that event, they found a density of approximately 0.08 electrons per cubic centimeter. That number matched expectations for the local interstellar medium, confirming that Voyager had crossed into interstellar space. But the measurement was only the beginning. In the years that followed, additional shock waves reached the spacecraft. Each one produced a similar pattern. First, the plasma around Voyager compressed, then the plasma wave instrument detected oscillations. Finally, scientists calculated the surrounding density, and each time the value increased slightly. By 2018, the measurement suggested densities approaching 0.11 electrons per cubic centimeter. At first glance, the difference might appear small. But consider the scale involved. Voyager had traveled only a few astronomical units beyond the heliopause when those changes were detected. In galactic terms, that distance is extremely short. If density is increasing across such a small region, it suggests the spacecraft may be moving through a larger structure where gas is gradually compressed. Several possibilities exist. One explanation involves the heliosphere itself. Although the heliopause marks the boundary where solar wind pressure balances the interstellar medium, the Sun's influence may extend farther than that simple boundary suggests. The heliosphere moves through the galaxy as the Sun orbits the center of the Milky Way at about 220 kilometers per second. As it moves, the heliosphere pushes against the interstellar medium, potentially creating a compression region ahead of it. Similar to the way a boat moving through water creates a bow wave, Voyager's trajectory may be passing through part of that compressed region. Another possibility involves the structure of the Local Interstellar Cloud. The solar system is currently traveling through this cloud, which contains slightly denser gas than the surrounding interstellar medium. Astronomical observations suggest that the cloud may contain variations in density and magnetic pressure. Voyager might simply be encountering a denser portion of that cloud. Magnetic fields could also play a role. Interstellar magnetic fields are weak, typically around a few microgauss, far weaker than Earth's magnetic field. Yet across enormous distances, even weak fields can influence how plasma moves. If magnetic field lines become compressed or twisted near the heliopause, they could concentrate plasma along certain regions, producing the density gradients Voyager is detecting. For now, scientists continue studying the data. Every time a new solar eruption sends a shockwave outward through the heliosphere, researchers watch carefully to see whether Voyager will detect another plasma oscillation. Each new measurement adds another point to the map. Slowly, over years, those points are revealing the shape of the interstellar environment surrounding our solar system. So far, we know that Voyager crossed the heliopause in 2012. We know that plasma density outside the heliosphere is higher than inside, and we know that density appears to be increasing along Voyager's path. But the pattern raises a deeper question, because if interstellar plasma is gradually compressing beyond the heliopause, something must be shaping that region on a much larger scale. The heliosphere itself may be responsible, or the solar system's motion through the galaxy may be creating structures we have never measured before. To understand the cause, scientists began examining the larger environment surrounding the Sun. Not just the boundary of the heliosphere, but the shape of the entire bubble that protects the solar system as it moves through interstellar space. Because Voyager may not simply be drifting into empty space, it may be traveling through the outer wake of the Sun's influence. By the late 2010s, a quiet pattern had begun to emerge in the data from Voyager 1. At first, each plasma wave detection looked like an isolated event. A solar eruption would launch a shock wave into space. Months or years later, that shock would reach the spacecraft, briefly compress the surrounding plasma, and trigger oscillations that the plasma wave subsystem could measure. Scientists would calculate the density, then the signal would fade, and Voyager would return to silence. But when researchers placed those measurements side by side, something unusual appeared. The numbers were slowly increasing. The first clear density estimate after the heliopause crossing in 2013 measured roughly 0.08 electrons per cubic centimeter. Later events produced slightly higher values, then higher again. By 2018, Voyager's measurements suggested densities approaching 0.110 electrons per cubic centimeter. The difference was small in absolute terms. Even at the higher value, interstellar plasma remains extraordinarily thin, but the trend was consistent enough that scientists began asking whether Voyager was encountering a gradual compression of the interstellar medium. That possibility was unexpected. For decades, astronomers believed the Local Interstellar Cloud, the region of space surrounding our solar system, was relatively uniform. Observations of nearby stars suggested that the density of interstellar gas near the Sun was low and stable, typically around 0.05 to 0.1 particles per cubic centimeter. Voyager's numbers were already near the upper end of that range. If they continued rising, it would suggest that the spacecraft was entering a region where the gas was becoming noticeably denser. But before jumping to conclusions, scientists had to consider how the measurements were being made. Voyager cannot continuously measure plasma density. Instead, density estimates come only when shock waves from solar eruptions compress the plasma enough to create oscillations. Those events are rare. Sometimes several years pass between them. That means the density profile is built slowly. Each new measurement represents a single snapshot along Voyager's path. Still, the snapshots were forming a pattern. To understand why, researchers began examining the structure of the heliosphere itself. The heliosphere is not a perfect sphere. As the Sun moves through the galaxy, the the solar wind pushes outward in all directions, but the interstellar medium pushes back. Because the solar system is traveling through space at roughly 26 kilometers per second relative to the surrounding interstellar gas, the heliosphere likely becomes distorted. The front side, facing the direction of motion, compresses slightly. The trailing side stretches into a long tail. Some scientists compare the shape to a comet, with the Sun near the center and the heliosphere trailing behind. Voyager 1 is traveling roughly toward the upwind direction, the direction from which the interstellar medium flows relative to the Sun. If the heliosphere compresses plasma ahead of it as it moves through the galaxy, Voyager may be traveling through a region where interstellar gas has already been pushed slightly closer together. Imagine a boat moving slowly across calm water. Even at modest speeds, the bow of the boat pushes water outward and upward, creating a gentle compression wave in front of it. Something similar may be happening as the heliosphere moves through interstellar space. The Sun's magnetic bubble could be compressing plasma over enormous distances. Voyager's increasing density measurements might reflect that compression. But that explanation is not the only possibility. Another factor involves the local interstellar cloud itself. The solar system is not traveling through empty space. It is currently passing through a region of gas and dust roughly 30 light-years across. This cloud contains mostly hydrogen atoms, along with trace amounts of helium and heavier elements. Astronomers know about the cloud because it leaves subtle signatures in the light from nearby stars. As starlight passes through the cloud, certain wavelengths are absorbed by atoms in the gas. By studying these absorption lines, researchers can estimate the density, temperature, and motion of the cloud. Those measurements suggest the local interstellar cloud has a temperature around 7,000 degrees Kelvin and a density close to 0.1 atoms per cubic centimeter. But those numbers represent averages across many light years. Within the cloud, density may vary from place to place. Voyager may simply be drifting into a slightly denser region of the cloud. If so, the trend might continue for years as the spacecraft moves through that structure. A third possibility involves interstellar magnetic fields. Magnetic fields exist throughout the Milky Way, threading through gas clouds and influencing how plasma moves. These fields are extremely weak compared to those found near planets or stars, typically only a few microgauss in strength. Yet across enormous distances, even weak fields can shape the distribution of plasma. Magnetic pressure can compress gas along certain directions while allowing it to expand along others. In regions where magnetic field lines converge, plasma density can increase. Voyager's magnetometer has measured the interstellar magnetic field since the spacecraft crossed the heliopause. The data suggest that the field near the heliosphere is somewhat stronger than expected. If those magnetic fields are squeezing plasma in certain regions, Voyager may be traveling through a corridor where gas has been concentrated. Each of these explanations remains possible, but the data alone cannot yet determine which mechanism is responsible. What scientists can say with confidence is that Voyager's measurements are revealing something real. The interstellar medium around the solar system is not perfectly smooth. It has structure. It contains gradients, and those gradients appear to extend beyond the heliopause. This realization has important consequences. For decades, the heliosphere was treated as a boundary separating the solar system from a relatively uniform interstellar environment. But Voyager's data suggests that the boundary may be embedded within a larger system of interacting forces. The Sun's magnetic bubble does not simply end. It interacts continuously with the surrounding interstellar medium. Plasma flows, magnetic fields twist, gas clouds drift slowly through space. All of these processes combine to shape the environment just beyond the heliosphere. Voyager 1 happens to be traveling directly through that region. Every year the spacecraft moves another 500 million kilometers farther from the Sun. Every year the interstellar medium around it changes slightly, and every time a solar shot wave reaches the spacecraft, the plasma briefly reveals its density again. Each measurement is small, each one takes years to arrive, but together they are building the first direct map of the region between the heliosphere and the surrounding interstellar cloud. So far we know the plasma density beyond the heliopause is gradually increasing, but understanding why requires looking at the heliosphere not just as a boundary, but as a moving structure interacting with the galaxy. Because the Sun is not standing still, it is traveling through space, and the bubble surrounding it may be reshaping the interstellar medium far beyond its edge. For most of the 20th century, scientists imagined the heliosphere as something close to a sphere. A simple idea made it easy to visualize. The Sun sits at the center, the solar wind expands outward in all directions, and somewhere far away, the pressure of the interstellar medium pushes back just enough to stop that expansion. In that picture, the heliosphere resembles a round bubble floating in space. But the real structure is more complicated. Because the Sun is not stationary, it moves through the Milky Way at enormous speed, roughly 220 kilometers per second, as it orbits the center of the galaxy. More importantly for the heliosphere, the Sun is also drifting through the local interstellar medium at about 26 kilometers per second relative to the surrounding gas. That motion changes everything. When an object moves through a fluid even slowly, the fluid responds. Air flows around a moving airplane. Water divides around the hull of a ship. In each case, pressure builds ahead of the object and trails behind it. The heliosphere experiences something similar. The solar wind continues to push outward from the Sun in every direction. But as the heliosphere moves through the interstellar medium, the gas ahead of it resists that expansion. Pressure builds on the forward side of the bubble, compressing it slightly. Behind the Sun, the heliosphere stretches into a long wake. The result is not a sphere. It is more like a distorted shape moving through space, something closer to a teardrop or comet-like structure. This idea has existed for decades, but it became clearer after the launch of a spacecraft called IBEX, the Interstellar Boundary Explorer, in 2008. IBEX does not travel to the edge of the heliosphere like Voyager. Instead, it orbits Earth and measures energetic neutral atoms, particles created when charged solar wind particles exchange electrons with atoms in the interstellar medium. These particles travel in straight lines and can be detected by spacecraft near Earth. By mapping where these particles come from, IBEX can create an indirect picture of the heliosphere's outer boundary. The first maps surprised researchers. Rather than showing a simple spherical shell, the data revealed a strange, bright ribbon of energetic particles wrapping across the sky. The structure became known simply as the IBEX ribbon. Its existence suggested that magnetic fields in the surrounding interstellar medium were interacting with the heliosphere in ways scientists had not fully anticipated. Magnetic fields outside the heliosphere appear to wrap around the solar bubble, influencing how particles move near the boundary. That discovery forced scientists to reconsider the heliosphere's shape. Computer simulations began incorporating both plasma flows and interstellar magnetic fields. The models suggested that the heliosphere might not form a long comet tail after all. Instead, magnetic pressure could compress the trailing region, creating something closer to a croissant-like structure with two extended plasma jets. The exact shape remains uncertain. What matters is that the heliosphere interacts dynamically with the surrounding interstellar medium. The boundary Voyager crossed, the heliopause, is not a rigid wall. It is a shifting surface where solar plasma meets interstellar plasma. Beyond that boundary, the Sun's influence does not disappear immediately. Magnetic fields extending outward from the heliosphere may continue affecting nearby interstellar gas for many astronomical units. This possibility becomes important when considering Voyager's rising plasma density measurements. If the heliosphere compresses interstellar plasma ahead of it as it moves through the galaxy, Voyager could be traveling through a region where the gas has been gently pushed together. Even a slight compression over large distances could produce the density increase observed in Voyager's data. To understand how this might happen, imagine a snowplow moving slowly down a road. The plow does not stop snow instantly at its blade. Instead, snow begins piling up gradually in front of the vehicle. The farther the plow moves, the more snow accumulates ahead of it. Something similar may be happening with the heliosphere. As the sun moves through the local interstellar cloud, the heliosphere could be creating a mild compression region extending tens of astronomical units into interstellar space. Voyager 1 is moving through that region. The spacecraft crossed the heliopause in 2012 at roughly 121 astronomical units from the Sun. Since then it has travelled several astronomical units farther outward. That distance is still very close to the boundary in cosmic terms. If a compression region exists ahead of the heliosphere, Voyager might still be inside it. The density measurements increasing from 0.08 to 0.11 electrons per cubic centimeter could represent the gradual buildup of plasma in that region. Evidence supporting this idea comes from the behavior of the interstellar magnetic field measured by Voyager. When the spacecraft crossed the heliopause, scientists expected a dramatic change in magnetic field direction. Instead, the direction changed only slightly. This result puzzled researchers at first, but later studies suggested that magnetic field lines outside the heliosphere may be draped around the solar bubble. In such a configuration, the magnetic field near the boundary would remain aligned with the solar field inside the heliosphere. If those field lines are indeed wrapping around the heliosphere, they could also guide plasma flows in ways that concentrate gas near the boundary. Magnetic pressure could gradually increase plasma density along Voyager's path. But there is still another possibility. The structure Voyager is measuring might not be caused primarily by the heliosphere at all. Instead, the spacecraft may be encountering variations within the local interstellar cloud itself. This cloud is part of a larger region of gas called the local bubble, a vast cavity in the Milky Way likely created by multiple supernova explosions millions of years ago. Inside this bubble, several small interstellar clouds drift slowly through space. The solar system happens to be inside one of them, and these clouds are not uniform. They contain subtle density gradients, temperature variations, and magnetic structures that astronomers can only estimate from afar. Voyager's measurements offer something new. For the first time, we have a probe moving directly through one of these clouds, sampling its plasma environment from inside. That makes every density measurement valuable. Each new shock wave that reaches Voyager briefly illuminates the plasma around the spacecraft, revealing another piece of the cloud's internal structure. So far we know that the heliosphere has a complex shaped by solar wind, interstellar gas, and magnetic fields. We know Voyager may still be traveling through a region where plasma has been compressed by those interactions, and we know the spacecraft is moving through a much larger structure, the local interstellar cloud, whose internal properties remain only partly understood. But the story grows even larger when we consider how the solar system itself is moving through that cloud. Because the Sun is not simply drifting through empty space, it is traveling through a region of the galaxy filled with ancient gas shaped by long-forgotten stellar explosions, and Voyager is now measuring that environment directly, one plasma wave at a time. Long before Voyager 1 crossed the heliopause, astronomers already knew the solar system was not drifting through empty space. The Sun is traveling through a region of the galaxy filled with thin gas and dust. This region is part of a larger structure called the local bubble, an enormous cavity inside the Milky Way where the density of interstellar gas is unusually low. The local bubble is thought to have formed millions of years ago. Several nearby stars reached the end of their lives and exploded as supernovae, releasing vast amounts of energy into the surrounding gas. Each explosion sent shock waves expanding outward, sweeping interstellar material away from the region. Over time, those explosions carved out a cavity roughly 1,000 light-years wide. Inside that cavity, The gas is extremely thin and hot compared with the average interstellar medium of the galaxy. But the local bubble is not completely empty. Within it float smaller clouds of cooler gas, drifting slowly through the cavity, like patches of fog moving through a large valley. One of those clouds surrounds our solar system. Astronomers call it the Local Interstellar Cloud. The cloud is not enormous by galactic standards, roughly 30 light-years across, but it contains enough material to influence the environment around the Sun. Its gas is composed mostly of hydrogen atoms along with smaller amounts of helium and trace elements. The temperature inside the cloud is about 7,000 Kelvin. That may sound extremely hot, but the gas is so thin that the temperature reflects particle motion rather than heat in the familiar sense. Individual atoms move quickly, yet they rarely collide with one another. Because of that low density, the cloud remains nearly invisible. Astronomers discovered it indirectly by studying the light from nearby stars. When starlight passes through interstellar gas, specific wavelengths are absorbed by atoms in the cloud. These absorption lines reveal the chemical composition and motion of the gas between stars. By comparing observations from different directions in the sky, researchers gradually mapped the outline of the local interstellar cloud. Those measurements showed that the solar system is moving through the cloud at roughly 26 kilometers per second. At that speed, the Sun will eventually leave the cloud. But the process takes time. Crossing a region 30 light-years wide at that speed requires tens of thousands of years. On human timescales, the motion is barely noticeable. Still, the motion matters, because as the solar system moves through the cloud, interstellar gas flows toward the heliosphere from a particular direction, what scientists call the interstellar wind. From Earth's perspective, that wind appears to arrive from the direction of the constellation Scorpius. The flow is gentle compared with solar wind speeds, but it is steady. Hydrogen atoms and ions drift toward the heliosphere, interacting with the outer boundary where the Sun's plasma meets the surrounding medium. This interaction shapes the heliosphere. On the forward side, the direction the Sun is moving, interstellar gas presses against the heliopause. Behind the Sun, the heliosphere stretches into a long wake where solar wind continues flowing outward. Voyager 1 is traveling roughly toward the upwind direction of that flow. That means the spacecraft is moving into the incoming stream of interstellar gas. If the local interstellar cloud were perfectly uniform, the density Voyager measures should remain roughly constant, but the cloud is not perfectly uniform. Observations of nearby stars suggest subtle density variations across different regions of the cloud. In some areas, the gas appears slightly thicker. In others, it becomes thinner. Magnetic fields within the cloud also influence how plasma moves. Interstellar magnetic fields are weak, typically only a few microgauss, but over large distances they can guide the motion of charged particles. Plasma tends to drift along magnetic field lines rather than across them. Where those field lines converge or twist, plasma density can increase. Voyager may now be encountering one of those regions. As the spacecraft moves deeper into the cloud, the interstellar gas flowing toward the heliosphere could be gradually compressing ahead of it. The effect would be subtle but measurable. Each time a solar shock wave reaches Voyager and compresses the surrounding plasma, the plasma wave instrument reveals the density at that location. And those densities have been increasing. If the trend continues, it may indicate that Voyager is traveling through a gradient inside a local interstellar cloud, a region where gas becomes slightly denser over distance. Another possibility is that Voyager is approaching the boundary between two neighboring clouds. Astronomers suspect the solar system may eventually exit the local interstellar cloud and enter another nearby cloud known as the G cloud. The transition between these clouds could involve changes in density and magnetic structure. Voyager's path might intersect such a boundary. At the moment, however, The spacecraft has traveled only a few astronomical units beyond the heliopause, an extremely small distance compared with the size of the interstellar cloud. This makes interpretation difficult. The measurements reveal local conditions along Voyager's path, but they cannot yet map the entire structure of the surrounding cloud. Still, the data provide something unique. For the first time, humanity has a probe directly sampling the interstellar medium from inside it. Before Voyager, everything astronomers knew about interstellar gas came from remote observation. Telescopes could study absorption lines in starlight or emissions from distant nebulae, but they could not measure plasma density directly within the local environment around the Sun. Voyager changed that. Its instruments are now operating in a region of space that no spacecraft has visited before. The spacecraft is currently more than 24 billion kilometers from Earth, sending signals that take over 22 hours to reach us. Yet despite that enormous distance, its instruments continue to provide valuable data about the structure of the interstellar medium. Each plasma wave detection reveals another piece of the environment around the solar system. Each cosmic ray measurement shows how radiation moves through the galaxy. Each magnetic field reading helps scientists understand how interstellar fields interact with the heliosphere. Slowly, these measurements are transforming our understanding of the region between stars. So far, we know that the Sun is moving through the local interstellar cloud. We know Voyager 1 is traveling into the interstellar wind created by that motion. And we know the plasma density along Voyager's path appears to be increasing. But the cloud itself is shaped not only by gas flows, invisible magnetic forces stretch across it, guiding the movement of plasma and shaping the environment in ways that are difficult to detect from afar. To understand those forces, scientists turned to another set of measurements from Voyager, readings from its magnetometer, which has been quietly measuring the interstellar magnetic field since the spacecraft crossed the heliopause. Because between stars, even weak magnetic fields can reshape entire regions of space. When Voyager 1 crossed the heliopause in August 2012, one of the most closely watched instruments on the spacecraft was its magnetometer. The instrument had been operating since launch in 1977, quietly measuring magnetic fields around Jupiter, Saturn, and throughout the outer solar system. By the time Voyager approached the heliopause, scientists expected the magnetometer to provide a clear signal, confirming the spacecraft had entered a new region of space. Inside the heliosphere, the magnetic field originates from the Sun. The solar wind carries the Sun's magnetic field outward, stretching it across the solar system like long strands pulled by the flowing plasma. Because the Sun rotates, those magnetic field lines become twisted into a spiral pattern known as the Parker spiral. Near Earth, the magnetic field strength is usually around 5 nanotesla. Farther from the Sun, the field becomes weaker, but its structure still reflects the solar wind that carries it outward. Beyond the heliopause, however, the dominant magnetic field belongs to the galaxy. Interstellar magnetic fields form over enormous distances, shaped by the motion of gas clouds, shock waves from supernova explosions, and the rotation of the Milky Way itself. These fields are much weaker than planetary fields, typically measuring only a few tenths of a nanotesla. Yet across light years of space, even weak magnetic fields can influence the motion of plasma. Charged particles rarely move freely across magnetic field lines. Instead, they spiral along them. Over large distances, this behavior causes plasma to follow magnetic structures, concentrating in some regions while thinning in others. Because of this, interstellar magnetic fields can shape the density of plasma in the surrounding medium. When Voyager approached the heliopause, scientists expected the magnetometer to detect a sudden change in magnetic field direction, a clear sign that the spacecraft had left the Sun's magnetic environment and entered the galaxies. But the data did not behave exactly as predicted. The magnetic field strength increased slightly, yet the direction remained surprisingly similar. Instead of rotating sharply, the field direction shifted only modestly. At first, this puzzled researchers. If Voyager had crossed into interstellar space, why did the magnetic field still appear aligned with the solar magnetic field? The answer gradually became clearer. Magnetic field lines in the interstellar medium may be draping around the heliosphere. As the heliosphere moves through the local interstellar cloud, the surrounding magnetic field cannot easily penetrate the solar wind bubble. Instead, the field lines bend and wrap around the boundary, much like water flowing around a rock in a stream. In such a configuration, the interstellar magnetic field near the heliopause can appear nearly aligned with the solar field inside the heliosphere. Voyager happened to cross the boundary in a region where this alignment occurs. This discovery changed how scientists think about the heliosphere. Rather than a simple bubble with a clean magnetic boundary, the heliosphere appears to interact continuously with the surrounding interstellar magnetic field. The interaction creates regions where plasma becomes compressed or redirected. Those regions may extend several astronomical units beyond the heliopause, and that compression could explain the density increase Voyager is measuring. Magnetic fields exert pressure on plasma. In physics, this is known as magnetic pressure, and it arises because magnetic fields store energy. When field lines are compressed or bent, the energy increases, producing forces that push back against the surrounding plasma. In interstellar space, magnetic pressure can balance the thermal pressure of gas. Where magnetic fields strengthen or converge, plasma density can increase as particles are guided into certain regions. Voyager's magnetometer has measured the strength of the interstellar magnetic field near the heliopause at roughly 0.4 to 0.4 to 0.6 nanotesla. That value is slightly stronger than many earlier models predicted. If the magnetic field near the heliosphere is stronger than expected, it could compress plasma in the surrounding interstellar medium. Such compression would produce exactly the type of gradual density increase Voyager appears to be observing. But the situation may be even more complex. Magnetic fields are not static structures. They evolve as plasma moves through them. In the local interstellar cloud, plasma flows toward the heliosphere as the Sun moves through the galaxy. At the same time, the solar wind pushes outward from the heliosphere. Where these flows meet, magnetic fields can twist, stretch, and reconnect. This process can produce localized regions where plasma density changes. Some simulations suggest that interstellar magnetic fields may create narrow corridors where plasma becomes concentrated along certain directions. Voyager may be traveling through one of those corridors. The spacecraft's path is not random. It is moving roughly toward the direction from which interstellar gas flows toward the heliosphere. That trajectory places Voyager in a region where the interaction between solar wind, interstellar gas, and magnetic fields may be strongest. Each plasma weight measurement provides another clue about the structure of that region. So far, the data suggests that plasma density is rising gradually as Voyager travels farther from the heliopause. If magnetic compression is responsible, the density may eventually stabilize once the spacecraft moves beyond the region influenced by the heliosphere. Alternatively, the density increase may reflect larger structures within the local interstellar cloud. The two explanations are not mutually exclusive. Magnetic fields inside the cloud could be interacting with the heliosphere in ways that amplify density variations. Understanding that interaction is one of the most important scientific goals of the Voyager mission today. Because the heliosphere plays a crucial role in protecting the solar system, it shields Earth and the other planets from a large fraction of the galaxy's cosmic radiation. The shape and strength of the heliosphere determine how much radiation reaches the inner solar system. If the interstellar magnetic field compresses the heliosphere, the protective bubble around our solar system could change over time. That possibility becomes especially important when considering long timescales. The solar system does not remain inside the same interstellar cloud forever. Over tens of thousands of years, it moves into new regions of the galaxy, where plasma density and magnetic conditions may differ. Voyager's measurements provide a rare glimpse into those environments. For the first time, we are observing how the heliosphere interacts with the interstellar medium directly from the outside. So far, we know that the interstellar magnetic field near the heliopause is stronger and more structured than expected. We know that plasma density beyond the heliopause appears to be rising, and we know that magnetic pressure may be shaping that region. But there is another factor influencing Voyager's measurements. The Sun itself continues sending disturbances outward into interstellar space. Massive eruptions from the solar surface launch shock waves that travel for years before reaching the spacecraft. Those waves do more than trigger plasma oscillations. They temporarily reshape the environment around Voyager, and they reveal just how far the Sun's influence can reach into the space between stars. From Earth, a solar eruption feels local. A bright flash appears on the surface of the Sun. Within minutes, radiation reaches Earth and satellites detect a surge in energetic particles. Hours later, geomagnetic storms can ripple through Earth's magnetic field, sometimes painting the sky with auroras. The entire event unfolds within a day or two, but the full journey of that eruption is much longer. When the Sun releases a coronal mass ejection, billions of tons of plasma surge outward into space. The expanding cloud plows through the solar wind, forming a shock wave that spreads across the heliosphere. Close to the Sun, the shock travels extremely fast, sometimes over 1,000 kilometers per second. But as it moves farther from the Sun, it slows. The solar wind becomes thinner. The shock expands outward across an enormous volume of space. Its energy gradually spreads across a growing sphere. Yet the wave does not disappear. It keeps moving. Through the orbit of Mars, past Jupiter, beyond Saturn, out toward the distant boundary where the heliosphere meets the galaxy. Because the solar system is vast, the shock's journey can take more than a year. Sometimes it takes longer. Eventually, the wave reaches the outer boundary of the heliosphere, the heliopause. For a long time, scientists believed solar disturbances would weaken so much that they would barely affect the region beyond this boundary. Voyager's measurements changed that assumption. When powerful eruptions occur on the Sun, the shock waves they generate can travel all the way to interstellar space. And when those shocks arrive at Voyager's location, they disturb the surrounding plasma. The disturbance compresses the interstellar gas around the spacecraft. That compression produces oscillations, and those oscillations allow scientists to measure plasma density. In other words, the Sun is indirectly illuminating the interstellar medium. Every solar eruption that launches a shock wave into the outer solar system becomes a probe, a natural experiment that briefly reveals the structure of the gas surrounding Voyager. One of the most important examples occurred in 2012. A powerful solar eruption launched a shock wave that traveled outward for months. When the wave finally reached Voyager in 2013, it triggered the first clear plasma oscillations detected in interstellar space. Those oscillations revealed the density of the surrounding plasma, but the event revealed something else as well. The shock had traveled far beyond the heliopause. This meant the Sun's influence extended farther into interstellar space than scientists previously assumed. The heliopause marks the boundary where solar wind pressure balances the interstellar medium, but disturbances originating from the Sun can still propagate beyond that boundary. The shock wave carries energy through the surrounding plasma. Even after the solar wind itself has stopped dominating the environment, the wave continues traveling outward. Voyager's plasma wave instrument detects the effect. Over the past decade, several solar eruptions have produced similar signals. Each one sends a shock wave across the solar system. Each one eventually reaches Voyager. Each one briefly compresses the interstellar plasma around the spacecraft, and each one allows scientists to measure the density of that plasma. The process is slow. Sometimes years pass between measurements, but the data accumulate gradually. and each new signal strengthens the pattern researchers have been observing. The plasma density surrounding Voyager appears to be increasing with distance from the heliopause. This observation raises an intriguing possibility. The heliosphere itself may be influencing the structure of the interstellar medium over distances larger than expected. Imagine dropping a stone into a calm lake. The ripples spread outward far beyond the point of impact. Something similar may be happening with solar eruptions. Even though the solar wind loses its dominance beyond the heliopause, disturbances launched by the Sun continue moving through the surrounding plasma. Over long periods, repeated eruptions could influence the distribution of plasma near the heliosphere. The solar cycle adds another layer to this process. The Sun's activity rises and falls over an 11-year cycle. During active periods, solar eruptions become more frequent. More coronal mass ejections occur, and more shockwaves are launched into space. During quieter phases, eruptions become less common. Voyager's measurements may reflect the cumulative effect of multiple solar cycles sending disturbances outward into the interstellar medium. Each shockwave compresses plasma slightly. Over time, those repeated compressions may influence how plasma is distributed near the heliosphere. This idea remains under investigation. The interstellar medium is shaped by many forces simultaneously. Magnetic fields, gas flows, ancient supernova shockwaves, and the motion of the solar system itself. Solar eruptions represent only one influence among many. But Voyager has shown that the Sun's activity can reach farther than previously believed. Events that begin on the Sun's surface can travel over 120 astronomical units and still affect the plasma environment around the spacecraft. In practical terms, this means the heliosphere is not a static boundary. It is part of a dynamic system extending into the interstellar medium. The Sun sends disturbances outward. Interstellar gas flows inward toward the heliosphere. Magnetic fields thread through both regions, and Voyager sits in the middle of this interaction. Every few years, a solar eruption launched from the Sun reaches the spacecraft. The plasma compresses, the instrument listens, and for a brief moment, the invisible environment around Voyager becomes measurable again. So far, we know that solar shock waves can travel beyond the heliopause. We know they trigger plasma oscillations that reveal the density of the interstellar medium. And we know those measurements show a gradual increase in plasma density along Voyager's path. But even with these observations, many questions remain. Because the data still do not fully explain what is shaping the interstellar medium just beyond the heliosphere. The models scientists use to describe this region do not yet capture every detail. And some aspects of Voyager's measurements continue to resist easy explanation, which means the investigation is not finished. The spacecraft is still traveling, and the data it sends back continues to challenge what scientists thought they understood about the space between stars. By the early 2020s, Voyager 1 had been traveling through interstellar space for nearly a decade. The spacecraft was more than 150 astronomical units from the Sun, drifting through a region of space that had never been sampled directly before. Its instruments were aging, its power supply slowly declining, yet it continued sending data across a distance of more than 24 billion kilometers. Those measurements had already answered one major question. Humanity now knew where the heliosphere ended. But the data had also created a new puzzle. The plasma density beyond the heliopause was not behaving the way many theoretical models predicted. Before Voyager's crossing, scientists expected the local interstellar medium near the solar system to remain relatively stable over short distances. Density variations were assumed to occur across scales of light years, not across just a few astronomical units. Yet Voyager's measurements suggested something different. Each plasma wave detection appeared to show a gradual increase in density as the spacecraft traveled farther from the heliopause. The trend was subtle, but it was persistent. That persistence forced scientists to revisit several assumptions about the structure of the interstellar medium near the Sun. One of the first possibilities considered was instrument interpretation. Because Voyager does not measure plasma density continuously, the measurements rely on interpreting oscillation frequencies triggered by shock waves. If the shocks themselves behave differently in interstellar space than expected, they might produce signals that appear to show a density increase even if the surrounding medium remained uniform. Researchers examined this possibility carefully. They compared Voyager's plasma wave data with theoretical models of shock propagation through interstellar plasma. The analysis suggested that the density estimates were reliable. The oscillation frequencies matched the values predicted by plasma physics equations. This meant the density increase was likely real. The next possibility involved local turbulence. Interstellar plasma is rarely perfectly smooth. Magnetic fields, gas flows, and pressure gradients can create small-scale irregularities in density. Voyager might simply be passing through a turbulent patch of plasma where density fluctuates slightly. But turbulence usually produces irregular changes. Voyager's measurements appeared more systematic. The density values increased gradually over time rather than jumping randomly between higher and lower values. That pattern suggested a broader structure rather than isolated turbulence. Scientists then turned to simulations. Advanced computer models began incorporating detailed interactions between the heliosphere and the surrounding interstellar medium. These models included solar wind plasma, interstellar gas flows, magnetic fields, and the motion of the solar system through the galaxy. Some of these simulations produced an interesting result. They suggested that the heliosphere might generate a compression region extending outward into interstellar space. As the Sun moves through the Local Interstellar Cloud, the heliosphere acts like a moving obstacle in the flow of interstellar plasma. Gas approaching the heliosphere slows slightly and becomes compressed. That compression could extend several tens of astronomical units beyond the heliopause. If Voyager is still traveling through that region, the spacecraft would detect increasing plasma density as it moves farther into the compressed zone. Eventually, the density would level off once Voyager reaches undisturbed interstellar space. This explanation fits the general pattern observed in the data. But it remains difficult to confirm. Voyager provides measurements along only a single path through interstellar space. Without additional spacecraft sampling other directions, scientists cannot yet determine the full shape of the surrounding plasma environment. Another unresolved question involves the interstellar magnetic field. Voyager's magnetometer has measured the field strength beyond the heliopause at roughly 0.4 to 0.429 tesla. These values are consistent with earlier astronomical estimates, but the structure of the fields near the heliosphere appears complex. Magnetic field lines may be draped around the heliosphere, creating regions where plasma becomes concentrated. Such regions could produce density gradients similar to those Voyager is observing. However, mapping these magnetic structures requires more data than Voyager alone can provide. Then there is the possibility that Voyager is encountering variations inside the Local Interstellar Cloud itself. Astronomers know that interstellar clouds contain internal structures, filaments, density gradients, and temperature variations shaped by past stellar explosions and magnetic flows. If Voyager is entering a denser region of the cloud, the increasing density measurements could simply reflect the natural structure of that environment. But again, the limited number of measurements makes it difficult to distinguish between these possibilities. The spacecraft provides snapshots rather than continuous coverage. Each new plasma wave detection offers another data point, yet those events occur only when solar eruptions send shock waves across the solar system. Years may pass between them. This slow pace is one reason Voyager's mission remains scientifically valuable, even decades after launch. Every additional year of operation increases the distance between measurement points. Over time, the spacecraft will move far enough from the heliopause that scientists may finally see whether the density continues rising or eventually stabilizes. That future data will help determine whether the increasing density represents a local compression region or part of a larger interstellar structure. Until then, the puzzle remains open. Voyager's measurements have already shown that the region beyond the heliosphere is more structured than scientists once believed. It is not simply an empty void between stars. Instead, it is a dynamic environment shaped by the motion of the solar system, the influence of magnetic fields, and the slow movement of gas clouds through the galaxy. The spacecraft continues drifting outward through that environment. Every year it moves farther from the heliopause. Every year its instruments record new details about the plasma surrounding it. And every year the mission brings scientists a little closer to understanding the structure of the interstellar medium near our solar system. So far, we know that Voyager is detecting plasma waves in interstellar space. We know those waves reveal increasing density beyond the heliopause, and we know several physical processes could explain the trend. But the investigation is still unfolding. Because Voyager's power supply will not last forever, the spacecraft's instruments are gradually shutting down as energy becomes scarce, which means the time available to gather new measurements is limited, and that makes every remaining signal from the spacecraft more valuable than the last. Every instrument aboard Voyager 1 runs on a power source that is slowly fading. Unlike spacecraft near Earth, Voyager cannot rely on solar panels. At its current distance, more than 150 astronomical units from the Sun, sunlight is nearly 40,000 times weaker than it is near Earth. Solar panels would produce almost no usable electricity. Instead, Voyager carries a different kind of power supply. 3 devices known as radioisotope thermoelectric generators, or RTGs. Inside each generator sits a small quantity of plutonium-238, a radioactive isotope that releases heat as it naturally decays. The heat flows through thermoelectric materials that convert part of that energy directly into electricity. This system has powered Voyager since launch in 1977. At the beginning of the mission, RTGs produced roughly 470 watts of electrical power. But radioactive decay is constant. Each year, the amount of heat generated decreases slightly, and the spacecraft's available electrical power declines. Today, Voyager 1 operates on less than half of the power it had at launch. Mission engineers at NASA's Jet Propulsion Laboratory have spent decades carefully managing that shrinking energy supply. One by one, instruments have been turned off as power levels dropped. The spacecraft's cameras were among the first systems shut down back in 1990. Their job, imaging the outer planets, had already been completed. Other instruments followed over the years. Each shutdown was planned carefully. Engineers examined which systems were still producing unique scientific data and which could be safely retired. The goal was simple: keep the most valuable instruments operating as long as possible. Today, only a small set of instruments remain active. Among them are the plasma wave subsystem, the cosmic ray subsystem, and the magnetometer. These instruments continue measuring the interstellar environment surrounding the spacecraft. But their time is limited. The plutonium fuel inside the RTGs decays steadily, reducing electrical output by about 4 watts per year. To conserve power, engineers occasionally switch off heaters or non-essential systems, allowing the spacecraft to operate in colder conditions than originally intended. Some instruments now function at temperatures far below what their designers expected in the 1970s. Yet remarkably, they continue working. NASA estimates that at least 1 or 2 instruments may remain active until around 2030. After that, the spacecraft will no longer have enough electricity to power its scientific payload. Voyager will continue drifting through space, but it will fall silent. Before that happens, scientists hope to collect as much data as possible about the interstellar medium. Every year, Voyager travels another 3.6 astronomical units farther from the Sun. That steady motion is crucial. If the rising plasma density detected near the heliopause represents a compression region created by the heliosphere, Voyager should eventually leave that region. At that point, the density measurements would stabilize. Such a result would confirm that the heliosphere influences interstellar plasma over distances extending several astronomical units beyond its boundary. But if the density continues increasing, it may indicate that Voyager is entering a denser part of the Local Interstellar Cloud. In that case, the spacecraft would provide the first direct measurements of how plasma density varies inside the cloud. Either outcome would be scientifically valuable. The remaining years of Voyager's mission may therefore reveal whether the density trend observed since 2013 continues. Another key objective involves measuring cosmic rays. Beyond the heliosphere, Voyager's detectors are exposed to high-energy particles arriving from across the galaxy. These cosmic rays carry information about distant astrophysical events, supernova explosions, shock waves from stellar winds, and magnetic turbulence in the Milky Way. By measuring cosmic ray intensity over time, Voyager helps scientists understand how radiation moves through interstellar space. These measurements also help researchers estimate how effectively the heliosphere shields the inner solar system from galactic radiation. Understanding that protection matters. If the solar system moves into a region of the galaxy with higher plasma density or stronger magnetic fields, the heliosphere could shrink slightly, allowing more cosmic radiation to reach Earth. Voyager's data provide clues about how such changes might occur. Meanwhile, the spacecraft continues transmitting its signals back to Earth. Every year, Voyager's transmitter produces only 23 watts of power, roughly the energy used by a small refrigerator light. By the time those radio waves reach Earth, they are incredibly faint. NASA's Deep Space Network listens for them using massive radio antennas in California, Spain, and Australia. These antennas work together to maintain contact with the spacecraft as Earth rotates. Each signal takes more than 22 hours to travel from Voyager to Earth. A command sent from Mission Control requires nearly 2 full days for the round-trip conversation. Yet despite that distance, the spacecraft continues reporting its measurements. Each new data packet adds another piece to humanity's understanding of the interstellar environment surrounding the solar system. The remaining years of Voyager's mission will likely produce only a handful of additional plasma density measurements. Each one depends on a solar eruption sending a shockwave across the solar system. Those events cannot be predicted precisely. Sometimes several years pass between them, but when a shockwave does reach Voyager, the plasma around the spacecraft vibrates again. The instrument listens, and the density of the interstellar medium reveals itself once more. These rare signals are now among the most valuable pieces of data Voyager can provide. Because once the spacecraft's power supply fades completely, no other probe will be there to replace it. For now, Voyager remains humanity's only instrument operating in interstellar space. It is a fragile observer drifting through a region no spacecraft had ever reached before, and every additional year of operation pushes that exploration a little farther into the galaxy. So far, we know that Voyager has crossed the heliopause. We know that plasma density beyond that boundary appears to be increasing, and we know that the spacecraft may soon reveal whether that trend continues. But Voyager's journey also carries a broader meaning. Because this small machine, launched in the 1970s, is now measuring the environment between stars, a place humanity had never touched before, and its final discoveries may reshape how we understand the boundary between our solar system and the galaxy beyond it. At this moment, Voyager 1 is farther from Earth than any object humanity has ever built. The spacecraft is more than 24 billion kilometers away, drifting outward through the darkness of interstellar space. At that distance, the Sun is no longer the bright star we see from Earth. It appears as a brilliant point of light among many others in the sky. The planets are long behind it. Jupiter and Saturn exist only in Voyager's past, decades back along its trajectory. Even the distant Kuiper belt lies far inside the region the spacecraft has already crossed. Voyager is now traveling through the environment between stars, yet the spacecraft itself remains surprisingly small. Its central body is about the size of a compact car. A large dish antenna, 3.7 meters wide, faces back toward Earth, continuously sending radio signals across the solar system. Extending from the spacecraft are thin booms carrying scientific instruments and sensors. One of those booms holds the magnetometer, positioned away from the spacecraft to avoid interference from onboard electronics. Another set of antennas forms the plasma wave subsystem, which listens for electrical oscillations in the surrounding plasma. These instruments have been operating for nearly half a century. Many were designed using electronics that today would appear almost primitive, yet the systems were built with durability in mind. Engineers expected Voyager might operate for a decade. Instead, the spacecraft has remained active for nearly 50 years. Part of that longevity comes from careful management by engineers at NASA's Jet Propulsion Laboratory. Over time, they have reprogrammed Voyager to conserve power, shut down unnecessary systems, and adjust operations as conditions change. Commands sent from Earth take more than 22 hours to reach the spacecraft. Once a command arrives, Voyager executes it automatically. Then it begins transmitting the results back to Earth. Those signals travel outward at the speed of light. By the time they arrive at the deep space network, they are incredibly faint. The signal strength reaching Earth is less than 1/billionth of a billionth of a watt. To detect it, giant radio antennas more than 70 meters wide must listen carefully for Voyager's narrow transmission frequency. Despite that immense distance, the spacecraft continues to report its measurements. Each day it sends a stream of data describing the environment around it: particle counts, magnetic field readings, plasma wave signals, and cosmic radiation levels. These measurements represent the first direct observations ever made from interstellar space. Before Voyager crossed the heliopause in 2012, scientists could only infer the properties of the interstellar medium near the solar system. Astronomers studied distant stars and measured how their light changed as it passed through interstellar gas. Those observations provided estimates of density, temperature, and composition, but they remained indirect. Voyager changed that. The spacecraft is now physically inside the interstellar medium, measuring conditions directly with onboard instruments. Its observations have confirmed that the region beyond the heliopause contains a denser plasma environment than the solar wind inside the heliosphere. They have also revealed that the interstellar magnetic field near the heliosphere has a complex structure, likely influenced by the interaction between the Sun's magnetic bubble and the surrounding gas. Most intriguingly, Voyager has detected plasma waves that suggest the density of interstellar plasma increases gradually along its path. That observation remains one of the most unexpected findings of the mission's later years. It hints that the heliosphere may influence the surrounding interstellar medium over distances larger than previously believed, or that the local interstellar cloud contains density gradients that scientists had not yet measured directly. Voyager alone cannot answer every question. The spacecraft follows a single trajectory through interstellar space. Its instruments sample only the environment immediately around it, yet even this narrow path provides valuable insight into the structure of the region surrounding our solar system. Every additional year of data extends the distance between Voyager and the heliopause. Over time, scientists will be able to determine whether the density increase near the boundary eventually levels off or continues deeper into the interstellar medium. Meanwhile, Voyager's cosmic ray detectors continue measuring high-energy particles arriving from across the galaxy. These particles originate from distant supernova explosions, stellar winds, and shock waves traveling through interstellar gas. Inside the heliosphere, many cosmic rays are deflected by the sun's magnetic field. Beyond the heliopause, that protection weakens. Voyager's measurements show that cosmic ray intensity increases significantly outside the heliosphere. This confirms that the solar wind bubble acts as a protective shield around the solar system. Understanding that shield matters. The heliosphere reduces the amount of galactic radiation reaching Earth and the other planets. Changes in the surrounding interstellar environment could alter the size and shape of that protective bubble. Voyager's observations therefore help scientists understand how the solar system interacts with the galaxy around it. Yet beyond its scientific role, the spacecraft carries another kind of significance. Attached to Voyager's side is the Golden Record, the gold-plated disc placed there at launch in 1977. The record contains images of Earth, sounds of nature, greetings from different cultures, and music from around the world. Its purpose was simple. If the spacecraft were ever encountered by another civilization far in the future, the record would offer a small introduction to the planet that built it. The chances of that happening are extremely small. Space is vast. Even traveling at 17 kilometers per second, Voyager would need tens of thousands of years to approach another star. But the record remains there, quietly traveling with the spacecraft as it drifts through interstellar space. For now, Voyager's role is not to deliver messages, it is to listen. Its instruments continue recording faint signals from the plasma around it. Vibrations triggered by shock waves that began on the surface of the Sun years earlier. Those vibrations reveal the density of the gas between stars. They provide clues about how the heliosphere interacts with the interstellar medium, and they help scientists understand the environment our solar system is moving through as it orbits the galaxy. Voyager does not see the interstellar medium. It hears it through tiny electrical oscillations detected by antennas built in the 1970s. Those signals travel across billions of kilometers back to Earth, and with each one, humanity learns a little more about the region beyond the Sun's influence, because the spacecraft may be small, but the region it is exploring is vast beyond imagination. If you could stand beside Voyager 1 today, the view would feel unfamiliar. The Sun would still be visible, but it would no longer dominate the sky. From that distance, it would appear as a brilliant star among thousands of others scattered across the Milky Way. The planets would be invisible. Even the faint glow of the zodiacal dust that fills the inner solar system would be gone. Voyager now moves through a region where the Sun is simply one star within a vast galaxy. The spacecraft drifts through interstellar space at about 17 kilometers per second, slowly increasing its distance from the heliopause each year. Around it lies the Local Interstellar Cloud, a thin mixture of hydrogen gas, plasma, and magnetic fields stretching across dozens of light years. To human senses, the region would appear empty, but it is not empty. The interstellar medium is more like a very thin ocean in a vacuum. Within it, atoms drift slowly. Magnetic fields stretch across enormous distances, and shock waves from distant events ripple through the gas. Voyager's instruments are detecting those conditions directly. The spacecraft cannot photograph this environment, yet its measurements reveal a structure that had previously existed only in theory. Plasma density beyond the heliopause is higher than inside the heliosphere. Interstellar magnetic fields interact with the solar bubble in complex ways, and along Voyager's path, the density of interstellar plasma appears to increase gradually with distance from the Sun. This pattern may indicate a compression region where the heliosphere presses against the interstellar medium as the solar system moves through the galaxy, or it may reflect the internal structure of the Local Interstellar Cloud, where subtle density gradients exist across vast distances. The data collected so far cannot yet distinguish between these possibilities. That uncertainty is normal in scientific exploration. For most of human history, the space between stars was considered almost featureless, an enormous emptiness separating one stellar system from another. Modern astronomy has revealed something different. Interstellar space contains gas clouds, magnetic fields, cosmic radiation, and shock waves traveling through the galaxy for thousands of years. Stars are born inside these clouds. Supernova explosions reshape them. Galactic magnetic fields thread through them, and every stellar system, including our own, moves through this environment as it orbits the Milky Way. The heliosphere is the boundary where our solar system interacts with that larger galactic environment. Inside it, the sun's solar wind dominates. Outside it, the interstellar medium takes over. Voyager 1 now travels beyond that boundary. Its instruments are measuring the conditions our solar system is moving through right now. That information may eventually help scientists understand how the heliosphere changes when the sun enters different regions of the galaxy. In denser interstellar clouds, the heliosphere could shrink slightly. In thinner regions, it might expand. These changes could alter how much cosmic radiation reaches the planets inside the solar system. Voyager's data therefore help scientists understand not only the structure of the galaxy, but also the environment that surrounds Earth. And the spacecraft continues moving. Every year, Voyager travels roughly 520 million kilometers farther into interstellar space. The distance between the spacecraft and Earth grows steadily. Radio signals now take more than 22 hours to cross that distance. Yet, the connection remains. Commands from Earth still reach the spacecraft. Data from Voyager still returns. As long as its power supply lasts, the spacecraft will continue transmitting information about the interstellar medium. Eventually, the electricity generated by its radioisotope power system will fall too low to operate the remaining instruments. One by one, the sensors will shut down. Voyager will stop sending data, but the spacecraft itself will continue traveling. With no power left for communication, it will drift silently through the galaxy for millions of years. Long after Earth's continents have shifted and new stars have formed in the Milky Way, Voyager will still be moving outward. Its antennas will be cold, its instruments inactive, yet the spacecraft will remain a small artifact of human curiosity, traveling through interstellar space. For now though, Voyager is still listening. Each time a solar eruption launches a shockwave into the outer solar system, that wave eventually reaches the spacecraft. The surrounding plasma vibrates. The instrument records the signal, and the density of the interstellar medium becomes measurable once again. Those faint oscillations carry information across billions of kilometers back to Earth. They reveal how the sun's magnetic bubble interacts with the galaxy around it. They show that the region between stars is not silent, not empty, but structured and dynamic. Voyager is a witness to that environment. A small machine launched in the 1970s, still sending messages from beyond the sun's reach. And with every signal it returns, the quiet ocean between stars becomes a little less mysterious.